Okay, so we're doing the lab today. The lab is all on thermal physics. So, and that's the topic I just basically we're discussing right now in Physics 10. And I know we didn't get to the, but I think the bulk of it is there. So we're going to talk about it in the lab, and that's really the idea behind it. Any questions? The lab from last time is due tomorrow, of course. This lab is going to be due on Friday next week. And it has a couple of things, this lab. It has an item that you do at home, and it has something that you do on GeoGebra too. So let's get into the instructions. Share. Oh, I need to first of all go with you guys on the actual instructions on the lab itself. Let me make sure it's open, because this is a little different. You have two files to actually download. You have the instructions, typical stuff that we do all the time. Okay. Now there is an Excel file. It's important that you have to have Excel installed on your computer. You really have to, you have several options, honestly, not just two, okay? Since you are a student in Norco, you should have access to the license free of charge from Microsoft. All you have to do is register your license for Excel under using your email, and it should activate fine. You should not have a problem with it, so you should be able to install it. That's option number one. Option number two also is that if for some reason the activation doesn't work, usually Microsoft offices give you a trial period, I don't know how much, like 60 days or something. So you should be able to get this Excel done and you should be fine. The third option, I'm not sure honestly about Google Docs, but I know for sure there is a free software called Open Calc. It's part of the Open Office suite. It's free. Okay, it's 100% free, and you should be able to open Excel files from it. Now, when you save it, you have two options. You can save it back into an Excel file, but you have to make sure to choose Excel, or you're going to save it back into an Open Calc. So that's really the options in there. I can list these things for you guys. Basically, the three options. Maybe, I'm not saying it is, because I don't really work with it that much. As a matter of fact, I don't work a lot with the Office suites, to be honest with you. But maybe open, what is it? Google Docs also can open this thing, can open Microsoft Excel. Okay. Granted, this is the new Excel version. It has the X at the end, but it should be open fine. It should work fine. Now, the easiest way to doing this is to actually go and download yourself a copy of Microsoft Excel. By the way, it's probably the best product among all of the Microsoft suite stuff, okay? Everything that you can think of that Microsoft has done, probably Excel is the best thing out there. So it's a good software to have, and it's a good skill to have for your labs later on in physics, for your labs in chemistry, for your, if you're majoring in accounting, it's actually a great tool for that too. If you're majoring in other fields other than science, it's a great tool there too. And for data analysis, regardless of where you are. So it's a great tool. Honestly, it's a very good tool. So that's probably the only thing that does not have any kind of blemishes in it, unlike Word, which has all kinds of other problems with it. So this is something that you will need to do this experiment, because you will see that some of the data are provided to you by that file. Some of the data, basically, you do the observations, you collect the data, and you put it in your table. Then you take that data and you put it to the Excel file. What the Excel file will do for you, it does two things. First of all, it fills the missing place. It's going to give you other data that you need to go back and put it back into the PDF file. And then it's going to generate graphs for you. So you need to go and look at that graph that it generates and pick up some data that you're going to complete also with it, your lab report. So that file is needed, okay? I locked it a little bit to make sure that you don't by mistake delete a cell or delete a formula, because there is all kinds of formulas on it. So, and I made sure that only the cells that are needed where to enter the information is going to work. That way, like I said, to prevent any kind of unfortunate problems. So where you, for example, delete a formula or delete something, and then at the end things don't work for you, and then you'll probably have a problem. okay? Or you may not just have deleted the formula, you may have altered it a little so that it gives you the wrong answers completely. So those are the two things. So you need to download both files, the instructions, and also the Excel file. So I'm gonna download, I think I have them, let me make sure I have them on my computer. I think I do, I mean, that's how I uploaded, but let me locate them. Let me put it this way. Let me locate the files, and they should be in Lab 7. And let me open them. Open Lab 7, the form, and open the Excel file, because at some point we're going to refer to it. So I need to open it and keep it open in the background. Okay. Other than that, everything is standard. I was going to require from you to upload a picture of the home activity, and I think it's a good idea that you do that. So, but if you don't do it, you're not going to be able to answer the question. So you really have to do the activity that you do at home. That is part of. So when you open the Excel file, let me go back into the share the Excel file so that we start with that first. So when you open it, it looks like this, okay? There are two sheets in it. There is a graph sheet that you'll need at some point, and there is a data sheet, okay? The data sheet has these fields that you can enter stuff in. If you go to anywhere else, you're not going to be able to do anything. And there is this field also that you can enter information in it. So basically, that's the stuff that you're going to do in here. You're going to have all of this information. The temperature, the angle in degrees, the temperature, the angle in degrees. You're going to have 10 pieces of data that you're going to collect. And they're from 3 all the way to 12. That's 10 pieces. And then once you do that, you're going to look. This will be filled for you by Excel. This side will be filled for you. And this also will be filled in here where it says divide by 0. It's going to be filled also for you. And then you come in here to the chart, and the chart will give you the plot and how the curve would look like, okay? And also, it's going to give you something called R squared, okay? It's going to give you actually the formula, the fitting, the trend line, and it's going to give you next to it the value of R squared. You're going to read that number of value of R squared, and it's going to look something like this, okay? I'm going to just write a number in here. It's probably going to look like maybe, okay? 9, let's say, for example, 8.7 E negative 1, okay? You can put it as is, okay? If that's the case, just put the whole thing, however, the value that it gives you in there. But remember, if it's going to give you an E in it, and it says capital E, you have to write it as capital E, because I think it's not going to work with a lowercase e, but I'm not sure, okay? Like I said, I'm not really. So let's try it E negative 1. Okay, it works the same. Good. So if you make a mistake, for example, and you make it lowercase e, that's fine. It should work the same. So now it filled the rest, and it tells me that I have 13% error. Obviously, that's not the number I probably will get. I will get maybe a different number in here, okay, when I come in here. So R squared is going to be given in here. So all I have to do is copy it in here, okay? And the other values that I have in here, they will come actually from the actual experiment. So I need to fill these values in here from the actual experiment. So we started with the Excel file. You will need the Excel file as part of your also upload. So when you're done with your lab report and you need to upload your lab report, upload the lab report, and upload also the file that you have filled yourself. That means that after I am done with this file, I need to save it. Okay, just like we normally do with the PDF file. Because if you don't save it, it's going to come back blank like this one. So it doesn't, I don't know where you get these numbers from. Do you understand? So I need to know connection between your numbers and those that are coming from your table that you're going to come back to in terms of the PDF file. Are we clear on terms of the Excel file, at least of how it works? So when it opens, it defaults to the graph. There are two basically sheets in it. It's a workbook with two sheets. You really need to be in the data sheet. But before you even get there, you need to do the actual lab first, get all of your data. Once it's there, then you go to the Excel file. The Excel file has a lot of things, lots of information. It's going to give you 10 more pieces of data that you will need for your lab report. And it's going to give you the error, and it's going to give you R squared. Okay? So it's going to help you a lot in doing your lab without having to actually do calculations on your own. So it's a very useful file. Is this clear? So it's at the end, not in the beginning. Okay, I know I started with it, but just to clarify that. Okay, let's get into the, and it's needed as part of the lab report, okay? Let's get into the actual lab instructions as typical. Please do not forget about the rubric. It tells you how everything is graded, and every lab has its own grading rubric. So it's not the same for everything. I mean, there is a common thing. Objective is graded, the name is graded, the questions are graded with the same amount, all of this, and the conclusion has that. Sometimes, like in this case, we have a file upload, so that file also is uploaded. Some cases we have tables, and sometimes we have a lot of tables, and today we are fortunate since we only have one table. So we're lucky, and that table is graded depending on the number of cells in it, okay? So that's basically in terms of the rubric, and hopefully you guys have learned that by now. Again, the name. This is all on thermal physics. It starts with the specific heat. Basically, what the specific heat is, if you heat up an object, water, for example, its temperature starts to rise. How much temperature it rises, delta T, is proportional to how much heat you're going to get exposed to. So if you put it under the furnace, for example, for 5 minutes, it's going to get a certain amount of heat. If you put it under the furnace for 5 hours, it's going to get more heat. So that's basically what this thing is, because the furnace is providing an amount of heat per second. So it's actually a power. Okay, it's providing a power, and that power is a heat consumed for every second. So again, if you wait for a few seconds, it's going to give you less heat than if you wait for a long time. Now that heat, if you wait a long time, the temperature will rise drastically. Okay, delta T will be higher. Delta is the change, okay? Obviously, it depends on how much water I have already. If I have a small amount of water, the temperature will rise even higher. But if I have lots of amount of water, I have to wait a long time for it to start boiling. So the mass matters. And this C is specific to the material. For example, for water, it has a specific heat that is almost 1. The heat is measured in calories. It's 1 calorie per gram per degree Celsius. And the specific heat was defined based on water, okay? If you take water at 14.5 degrees and you heat it so that its temperature now is 15.5 degrees, then by definition, that is a 1 calorie. That's how the calorie was defined, based on water. So for water, it's 1. But that water has to be sitting specifically at 14.5. Now water, of course, changes a little, so the number is experimentally sometimes can be a little off than 1, okay? Water has a very high specific heat. In other words, water takes a lot of heat for its temperature to rise a little or drop a little. That's why if you happen to have food, for example, soup, for example, where it's off of the oven, when it's covered off of the stove, it's going to be very hot and it stays hot for a long time. Compared to the spoon, for example, you were stirring with. Let's say, for example, you put the spoon on the sauce and you were stirring with it, and now when it's done, you turn off the oven and you take the spoon and you put it aside, and you come back 10 minutes later, you find the spoon is almost cold, but the soup is still hot. And that is because water, which is the main component of any soup or any food for that matter, has a very high specific heat, so it retains a lot of heat. It doesn't lose it as easily as other things, okay? So that's why it's actually used for cooking things. That's why you boil eggs in it, okay? It makes it easier to do that. It takes a lot of heat and basically dumps it on the egg. Okay? And the egg is mainly water too, okay? So that's one thing, but we're not going to be exploring this expression in this lab. The other thing also is the conductivity, thermal conductivity of materials, okay? By the way, this whole lab that I have before you was part of a huge lab that I basically broke it down into just a couple of activities in here. So we're doing only a few things off of it. So again, in this, the other expression, basically, again, if you take a spoon and you put it on the oven and wait for a few minutes, on the furnace, the heat, you start to feel the heat coming through the spoon, okay? And that is because heat is moving along the spoon, okay? You have to be careful with that because that's going to get very hot very quickly because heat is transmitted. Any material transmits heat. It doesn't matter. So if you heat it from one side, it's going to transmit it. But some are better than others. Some materials are good conducting heat. They're good conductors of heat. Some of the others are poor conductors of heat. Good conductor of heat usually is a good conductor of electricity, like iron, for example, or copper. Okay, and the expression for that is the power, which is the rate at which heat is being dumped from one side to the other, is proportional to how long is a material. The longer it is, basically the more power is going to be transmitted. If it's short, it's going to be less. And depends also on the area. Okay, if the area is narrow, you're going to squeeze more heat on it than if the area is basically the rate. I'm not talking about heat, the rate at which the heat is moving. And of course, the higher the gradient in temperature, the higher this rate is. So the power, again, if the outside temperature is very high compared to the inside, you will have a lot of losses in this case of heat. And every material has its own conductivity. So some materials are poor conductors, some materials are good conductors, okay? Glass, for example, is a poor conductor, relatively speaking, than metal, okay? So that's some of the properties that we have in here. Okay, question 1. This is a task that you need to do at home. In your home, locate 2 objects similar with roughly similar thickness. A wooden spoon, for example, with a metallic spoon, okay? One made out of different materials, okay? One of them is metal, the other one is probably made out of wood, okay? One made from wood and the other out of metal, such as iron or aluminum. So it doesn't have to be spoons, whatever you can find at home, as long as they are similar in thickness, okay? And similar in size, more or less, okay? These items could be from the kitchen, okay? Let them sit next to one another. They don't touch next to one another, okay? For a long time. How long is it? Whatever you can. An hour, half an hour, doesn't matter, okay? As long as they stay long enough so that they are in equilibrium with their environment. If you're doing this in the kitchen, in the kitchen. If you're doing this in the living room, in the living room. Make sure they sit next to one another, not necessarily touching, but just next to one another for a long period of time. Then, using your hand, okay? Feel them. Feel the material made out of wood and the material made out of metal, okay? Which one do you think is cooler? Which one feels to you cooler? With the touch, okay, to the touch. You're going to tell me that, okay? And then, which is actually cooler? So there are 2 things in here to this question. Which one feels cooler to the touch, and which one is actually cooler? You guys understand? There are 2 parts in this question. Which one? Yes.
No, I'm just saying it's like, it's kind of hard. How can we measure which one is cooler?
To the touch.
Okay, so the one that feels cooler is cooler? Is that what? No?
No. Okay. So you don't have thermometer and you don't need thermometer for this statement, okay? So you're right. I mean, how do I measure? How do I know which one is cooler? Which one is actually cooler, okay? So the touch is fine. I can go with you and I agree with you, so I have no problem with it. I'm going to touch them, and one will probably feel cooler for me, and I'm going to tell you which one is cooler based on my touching. But what I said in here, the key word in here, let them sit in their environment for a long time. Who do you think is going to be cooler? Which one is going to be cooler when they sit next to one another for a long time in their environment? Or are they going to be difference in coolness? Is one of them going to be actually cooler than the other? I'm asking everybody now. What do you guys think?
I would say that the metal would be cooler.
Probably it's going to feel cooler. I agree with you. Maybe, okay?
Yeah, like feel cooler, yeah, that's what I meant to say.
Okay. Amanda is saying wood is going to feel cooler? Okay. Patricia probably also. Amanda, it's not measuring. It's just feeling, okay? Feeling them with your hand. Clear? So just to see which one feels cooler. That's the first part, okay? The second part of the question, which one is cooler, or are they the same?
Sorry, for some reason I was thinking we were heating them and then touching them. Okay,
don't
so
hit
just
them.
at
Okay.
a regular temperature. Got it.
Ouch.
Yeah, so definitely the metal will feel cooler.
Okay, good. So the metal, I think there is a consensus in here, and probably you guys are right, okay? But the second part of the question is the one I am seeking answers to. Which one is actually cooler? Or is there a difference in their temperature without using thermometer?
I think they're the same, right? Same masses, but they're different material.
The mass should not matter, honestly, okay?
You know
So
what?
the key word in here, they set in their environment for a long time. Are they going to be different?
I think it is going to be different because if you set both the wooden and the metal in the same environment for 30 minutes, earlier you did say that metal was a high, metal is a higher conductor of heat.
Yes.
Yeah, it's a higher conductor. So if it sits in the same environment, it would accumulate more heat over time, which would therefore make the ice cube melt faster. So that's what I think.
No, forget about the ice cube for right now. So let's keep, okay, forget about the ice cube. I'm talking just specifically in terms of them. Okay, they set there for the environment. Let's assume they reach a equilibrium with the environment. Samantha thinks it's the same. Does anybody? And also Patricia thinks it's the same. And I think they are correct. Let me tell you why they are correct, okay? Our feelings have nothing to do with it, and we'll explain the feelings. It has to do with the eyes, the second part, okay? Since they sat in the environment for a long time, they must have reached the equilibrium with the environment. So whatever the environment, the temperature is, they both have it. So one of them is a better conductor than the other, has nothing to do with how much temperature they are. And if you don't trust me, just bring a thermometer now and see if you can measure their temperatures. And you will see that they're actually the same temperature, okay? If you have one of those guns in there, the thermal, I have one, but I don't know what it is right now. The thermal gun that you can aim it at both of them after they wait for a long time, they will actually give you the same reading for both of them. And although one, and I agree with you guys, that feels cooler than the other, which brings us to the second part of the equation, which is when you put ice on them, okay? Place an ice cube or equal amount of crushed ice. Okay, so if you don't have an exact size of an ice cube, if you do an ice cube, it's going to take a long time. So I would probably get some crushed ice and take half, probably a teaspoon, and put it on both of them and observe and wait, okay? One of them will melt faster than the other. Okay, we didn't do this experiment. If we were in the lab, actually, we'll do this. But what do you guys think will melt faster? And this has to do with Jeffrey's earlier, basically mentioning the conductivity thing. Which one would melt faster, you're thinking? Because remember, ice has a lot of, has, if you wish, less kinetic energy than its surrounding. And it's going to give it to the environment now. Which material will take basically heat from the environment and dump it on the ice faster than the other, wood or metal?
Metal.
Yes. So we expect that actually it's going to melt faster on the one that felt cooler, okay, than the other one, than the wood one, okay. So it's a good thing to do. Try it at home. Try to get the same amount of crushed ice and watch, okay? Thank you, Amanda, too. Okay, so that's basically how we expect it, okay? So if they're the same, that's a surprise, okay? That probably you did not get them in the same environment or you didn't let them. So one of them will definitely melt faster than the other one, and that should be the metal, okay? And the reason why you actually felt one cooler than the other, because the metal was extracting more heat from you and it felt cooler because your hand now is losing a lot of heat compared to the wood that did not extract as much heat from your hand, It's a poor conductor, so it's not extracting a lot of heat from your hand, doesn't feel as cool. So what we feel is cool is actually has nothing to do with the temperature. The temperature is both the same, but we would have a feeling that one of them is cooler than the other, okay? Does this question make sense now to you guys? Everybody? So it relies on you to please do this experiment, okay? I'm trusting that you guys will actually do it at home. You explain your results. It has to do with this K. All of it has to do with the K. Okay? Here are some specific heats and some Ks for you, okay? The air has a specificity of 0.2 calories per gram per degree centigrade, per degree Celsius. And the air is a poor conductor. And it's good that it's a poor conductor, but it conducts heat nonetheless. And we're not talking about convection here, just talking about the air by itself, okay? Pure conduction. And aluminum, it has a very high conductivity, which is a good conductor. Look at the ratio, the difference between it. Let's compare, for example, aluminum, iron, or steel, which is 130, which is not as good of a conductor as aluminum, for example. Let's see here, do we have wood in here, typical wood? Look at the conductivity of wood, 0.5 compared to, let's say, for example, steel or iron-made spoon, or sometimes they make them out of aluminum, okay? So that's basically what you're dealing with. So this is the whole thing in here. So in your answer, you're probably going to refer to this table in here. Depending on if you've used an aluminum-based, it feels lighter, okay, the aluminum spoon, okay, versus that of iron. So if the iron, it's probably an alloy, a combination of other things too, okay? So question 2. It's related to question 1, actually. Suppose you're going to defrost some meat from for dinner tonight, okay? You have a nice 2 pounds, very good meat, okay, that you want to cook tonight, okay? Would you be better off defrosting it, of course wrapped, okay, we don't want to mess up the meat, by laying it on a wood cutting board, which is another option for you by doing this experiment on a wood cutting board, especially if it's small enough, and maybe another one made out of metal, okay? That's another way of doing it instead of doing it spoons, okay? So don't have to do spoons for this experiment. Or in a metal dish. Which one brings it faster to room temperature, thawed faster than the other? Explain. Of course, people who are basically used to kitchen stuff, probably they know the answer to this already, but I want you to think about it. You don't have to do this experiment, okay? You don't have to actually thaw the meat for it, okay? This is just a thought experiment. Do you guys know what this task is? So it really relates to the first one. Before going any further, does anybody have any suggestion as an answer to this question? Okay, Amanda seems to be on the right track. Does everybody agree with her, or she's by herself on this? Okay, Jeffrey agrees with you, so we're okay now, okay? So I suspect that's the same thing. And again, the explanation has to do with this table. Okay, typical wood, 0.5. Typical metal, for example, if you take it iron made, iron base or aluminum base, this is the number for the conductivity, okay? So now you know, if you're gonna defrost some chicken or some stuff, don't put them on the wooden cutting board, okay? That's not gonna be, it's gonna take a long time unless you really have to go shopping for other things. You forgot, for example, to get some of the, I don't know, some lemons, for example, to do the stuff. So probably put it on wood there or leave it back in the refrigerator. Okay, we talked about the concept of temperature in class. And that's actually one of the tasks for physics 10 people, is that to get this distinction between the two, okay? The formal definition of temperature is the change. This is a very, very complicated definition, so ignore that for right now, okay? The formal definition of temperature is that it is the change in internal energy per unit entropy at constant volume, or change in enthalpy per unit entropy at constant pressure. The problem is that this definition is meaningless to you guys. So it's because this is probably the first time that you take this class, and it's actually not even for a calc-based class. This is for advanced people who are doing thermodynamics. But this is a formal definition, okay? So if you want to read, if you're curious, for example, and if, for example, you discover a flaw in the definition that we gave in class today, and probably it's making you lose sleep, okay? And you wake up in the middle of the night sweating, wondering what went wrong in that definition. Okay, come back to this here, read it again, and you should be okay. Then you can go back to sleep. Does any one of you have experience like this one? Or physics is not something you worry too much about? I'm a fan. Oh, Amanda, at least. Okay, I was thinking that nobody does, otherwise I would have felt offended because that's me only. Okay, so that's the formal definition. If not, go back to the definition we did today in class for physics 10. So the problem, okay, so a more meaningful definition is temperature is the average internal energy per atom. That's what we decided today it was, okay? So how fast the atoms are moving. And as a matter of fact, the calculation of Mr. Boltzmann early on related immediately to the kinetic energy of the atoms or the kinetic energy of the particles that makes us the substance immediately to the concept of temperature, okay? And the famous relationship PV equal to nRT because he found it to be equal to some other constant times the temperature, okay? Constant now, it bears his name, Boltzmann constant. Okay. Heat, this is any transfer of internal energy. Again, it's a process. Heat is different, okay? For physics 10, this was part of their discussion today in that they're supposed to distinguish between the two, okay? An internal energy is the total energy that includes basically the potential for the object to do work and for the potential of the object to do actually heat. And the definition is in here too, okay? What is, that's the question related to this stuff, okay? So we're gonna go back into these definitions, ignore the formal definition and go basically to the simpler definition for temperature, read heat, and answer question 3. So it's just basically going through a definition. So what is the difference between heat, temperature, and internal energy? That's part 1 of the question. Which is hotter, a red hot nail or a bathtub filled with ice? Okay, that was actually a question of the in the slides today too. The answer was the red hot nail. Okay, because it has supposed to be more. Okay, which has more internal energy now. That was actually similar to a discussion we had about the 10-liter water sitting at 20 degrees Celsius and another one sitting at 22 degrees Celsius, okay? The one that has more stuff of it must have more internal energy. And the same thing should go for this one in here. The bathtub filled with ice should have more energy, albeit it's ice water. But it has more of that material than the red hot nail. So in this case, the matter, how much matter you have, matters, okay? If the red hot nail were placed inside the bathtub filled with ice, does the ice absorb more, less, or the same amount of heat? It has to absorb the same amount of heat. There is a conservation of energy. So if heat is lost from the nail, where would it go? It goes to the ice. So there is no room for it to go anywhere else. So that's basically the answer to this question. Does this question make sense to you guys? I know some of you were not in class today because you were not part of this, the other class, but the others I'm worried about to make sure that they're okay with it too. Does this make question for everybody?
Kind of had. I didn't really understand it because one's like hot. I'm not really sure.
There are too many things in this question. Okay, let's go back again on it. Okay.
Yes.
There's so many things. So first of all, you're supposed to list the difference between these guys: temperature, heat, and internal energy. Okay? Yes?
Yep.
That should be easy. Just going through the definitions. And please, for a moment, I might even scratch this one in here. Where is that commenting tool in here that I have in here handy? This one. So probably ignore the formal definition for you guys. You're not going to be needing it. Can I have another one? Okay. Man, every time I have to do this now. Okay. And this part too. You're not going to be needing this stuff. Here is the stuff that matters. Okay. For you guys. So you're going to compare these things. Let me give another word probably that is maybe a little bit, hopefully it's going to clarify things, but I'm not sure. The temperature is a state variable. A system has a definite temperature. You can use a thermometer to find it. System has a definite temperature. Okay. System also has a definite internal energy. That is a state variable. System does not have heat. Heat is only involved in transition between state and state. So a state can be defined for a system with its own temperature, with its own pressure, with its own volume, with its own basically internal energy, and the rest of the other words that we didn't talk about in here, namely entropy and other things. But those that define a system specifically, heat is not one of them. Work is not one of them. Object can do work depending on the environment it's doing work on, or vice versa, the environment, how much work is doing on it. Okay. That's something that hopefully adds a little bit of clarification, that they characterize these two, internal energy and temperature, they characterize the state of the object, whereas heat is involved only in transition between state and state. Okay, which is hotter? Now it's clear in this case, a red hot nail or a bathtub filled with ice water. Ice water must be at 0 degrees Celsius. 270 degree Kelvin. A red hot nail, not only, which is iron, not only it's hot, hotter than boiling water, but it have reached a temperature where now it starts to appear red. It's emitting radiation. So now it's super hot, okay? Probably several hundred degrees Celsius, okay? For it to reach that point. It still did not melt though, because once it melts, that has changed state, okay? So it's several hundred degrees Celsius. It's hot, you cannot touch it. You touch it, you burn, okay? Which one is hotter? Which one is hot? In this case, it's this one. It's clearly the one that has several hundred degrees Celsius in it. Which one has more internal energy? We're talking a bathtub now, filled with, albeit they are moving slowly because they have 0 degrees Celsius, but they have a bunch of them. So they must have more internal energy than this guy, okay? Now, which one, now if I place a red hot nail inside the filled with ice, does the ice absorb more or less? By conservation of energy, it has to absorb the same amount of heat that the red hot nail would lose. So it doesn't absorb more. Where would that energy come from? Or less? If it absorbs less, where would the extra energy go? Okay, so that is the first law of thermodynamics that dictates that only the same amount of energy, okay, per the first law of thermodynamics. Does this make better sense now?
It does.
Okay. Everybody else, good? Thank you, V. So we can continue now. Okay, and Amanda and Samantha and everybody else on board. Of course, again, like I said, we're doing lab, we're not doing a test, so I'm not challenging you to go and research the answers. So that's why I'm going through them in detail in here. I'm hoping that you guys, when you do the activities, that sheds more light on them and you'll have a better understanding of what we're doing. That is the purpose of the lab, okay? Is to have a better understanding, of course, developing the hypothesis and the objectives and doing these things. That is part of the activities in lab and coming up with conclusions based on the data you collect and the understanding. Yeah, this is the actual stuff. This is actually calorimetry, which is another branch of thermodynamics that we don't do in this lab, and that is to measure relative specific heats. And it's a very much involved lab. That takes at least a couple of hours to basically complete the data for it. But again, we're not doing that. We're doing thermal expansion. And the thermal expansion is basically the following. If you take a rod, I know this is not metallic, okay? Technically, it has to be a metal, okay? Otherwise, this will burn, actually start to melt if we put it under a furnace. You fix it from one end and you let it free from the other end so that you measure its length. You measure its length now and you heat it, provided you know how much heat you're putting on it, okay? So, I'm sorry, I don't have to know how much heat. I need to know how much difference in temperature. What is its temperature now before I heat it? And monitor the temperature with the temperature gauge, read the temperature as it changes, and measure it. And I see that it's going to go longer and longer, to become longer and longer. That is delta L, how long it's going to be compared to before. Let's say, for example, before it was 36 centimeters long. When I put it under heat, now it's 39 centimeters long. So that means it gained 3 centimeters in length. That is delta L, the change in length, not the actual length, 36 centimeters, 39 centimeters. That's not what we care for. We want just how much change in length, okay? Versus how much long it was before, which is L naught. L naught in this case, or L0, is the 36 centimeters that I started with. And the change in temperature is how much temperature, let's say, for example, initially it was sitting at 20 degrees Celsius, and now I had to raise its temperature to, let's say, for example, 37 degrees Celsius. So the change in temperature, delta T, is 37 minus 20, which is 17 degrees. So 17 degrees times the 36, and then I have in here 3. 3 divided by this number should give me the alpha. Alpha is a characteristic of the material. Different materials have different expansion rates, okay? And the table that follows actually gives you the alpha for different materials, okay? For glass, if it doesn't melt, because glass melts, it's 0.09, so it's going to, it has a very small alpha, okay? So you don't need a lot of temperature for it to increase, okay? To increase in length. Different kind of glass has a slightly higher number. Concrete, which is important as an engineer, I mean, civil engineer, you deal with this substance a lot, okay? You build buildings and things like that, and you have to be careful with the difference in temperature between cold winter, especially in the Midwest, not in here as much, and the hot summer. There is a big difference in temperature, and concrete will expand too. All materials do that too. So this is its alpha. For steel, again, we use beams of steel everywhere for construction, for everywhere. So this is its coefficient. For copper, it's this much. So this is an increasing order. Lead has the highest alpha in this case. It does not expand, or actually it expands more compared, relatively speaking, for the same amount of temperature, okay? So that's basically the different values that you have for alpha, okay? So again, it's a characteristic of the material. So this is what we will be measuring in this lab. We'll be measuring alpha, okay? So we will draw the curve delta L and delta T, okay? So we will measure delta L and we will measure delta T and divide the ratio of both of them. Actually, what we will be measuring is delta L over L naught, okay? And divide that by delta T and we will find alpha. Excel spreadsheet should give me how much alpha is, okay? If you go back into the spreadsheet, let me go back into it just to make sure that we're on the same page. This is alpha. It's going to be here. Once you fill out all of this data, it's going to give you an alpha already, okay? And it's going to be a power. That's why you see E here everywhere. Again, because the table itself has an E, and we're going to go back quickly to it. So it's going to give you that number. And if you look at the chart, it's going to give you the graph also, okay? And the graph should pass by the origin, but it will be slightly off, and that is because of the error, okay? So it's going to give you a line, and it's going to give you the equation of the line, and it's going to give you R squared. You take that R squared, and you plug it in here, okay? And you're in business now. So that's basically how the lab should work. So let me go back into the instructions. So we're going to actually do the objective now, since we know what we're doing. So that's left for you guys. Here is where the activity is going to be, okay? And in here, it's telling you what to do. So you're going to load the GeoGebra activity. Let's load it. Come back to it, okay? What is the link for it? Here. So I'm gonna load it. And let me make sure that it's loaded and sitting by itself. Here it is. Again, for some of you, probably if you are using maybe Chrome, don't try not to use it because probably you will have some stuff that is off with it. Okay, so let me go back into the instructions that you guys are on it because I changed to. Okay, then turn the flames on and watch both the temperature and the angle. Okay, collect 2 points for temperature and angles between 0 and 10 degrees. The degrees in here referring to the angles, not the temperature. Okay. Record the data in table 3. Let's look at quickly at table 3. Table 3 is a reflection of that Excel spreadsheet. So you're going to put the temperature in here, and you're going to put the angle in here. You do another one between 0 and 10 degrees, and you're going to collect them in here. So this number I expect it to be between 0 and 10 degrees, and this number is going to be between 0 and 10 degrees, okay? And then this number in here, the angle is between 10 and 20 degrees, and this angle is between 10 and 20 degrees. If this is, for example, 3, this could be 7, whatever you have data in there. If this is, for example, 12, this could be 18 or 16, depending on how much data it is. But I'm expecting these values to be between these 2 ranges. Since you have 5 ranges, I expect 10 points in here. So I have 2, 4, 6, 8, 10 pieces of data. So we need 10 pieces of data. Once you're done with this, then you take it to the Excel file and you copy this data. Okay, you copy it one by one in the Excel spreadsheet. Excel spreadsheet will give you this data. So you bring that data now from Excel spreadsheet to finish your table. Okay, you put it in here. Okay, and the Excel spreadsheet also will give you this number for alpha. Okay, and the Excel spreadsheet also will give you R squared that you copy from the graph. Actually, this is coming from the graph. And Excel spreadsheet will give you also the error. The error, you will not get it unless you do R squared. So when you get the R squared from the graph, you're going to plug it in here, and now your table is complete. Okay, so that is basically the biggest task in terms of the lab tonight. So let me go back to the GeoGebra now, the one that I clicked on, to see how we collect the data, because that's where you're going to spend most of the time tonight. So when you click on it, this is how it looks like. It doesn't look too much, does it? Okay, but you have to really be focused. That is the key in here. Okay, you have to be extremely focused on this one in here, because here is, does everybody first of all see everything in here? I have a word in here that says thermal expansion. I have this apparatus, which is the thermal expansion apparatus. On this side, it's fixed, okay? And on this side, it's going to expand, okay? It's going to move. As it moves, it's going to spin that arm on one way. In doing so, this thing will start spinning, will start going around, okay? And this provides heat. It's going to heat this rod, and as it heats it, it cannot move from this way. Actually, it's fixed from that side. So the only way for it to move is to move this way. In doing so, it's going to turn the needle, and it's going to give you how many degrees it has moved. So this is, we're supposed to go from 0 to 50 degrees only. We're not going to go beyond. So if you see the temperature going too high, you need to shut it off so that it cools down, okay? And this will give you delta T. So the two things that you need to be paying close attention to, and they vary very quickly, so you really have to be focused, okay, is these two numbers. So I'm gonna go turn on the heat and watch the degrees. I need a number between 0 and 10, okay? So I'm gonna turn on the heat and wait. Now it's good enough, probably it's 6 degrees, and this definitions in here was 6, okay? This is 2, 4, 6, 8, 10. I'm sorry, was it 4? It was 4 only, okay? So for temperature, that was 6. Again, I'm not really looking for too precise readings in here, as long as you can catch it between the two. So let's repeat it again. And you will see the fire actually coming on, okay? So I'm gonna go turn it on. Right now it's 4 degrees, and it was 6.37, okay? I looked at it quickly. So now I'm going to stop sharing the screen and go back in here to the other one. For my data, if I'm careful enough, this was 4 degrees and this was 6.37. 6.37. Okay. So I need another point between 0 and 10. So I'm going to go back into that one and turn it until the temperature is still below 10. Okay. So now 6, now it's 8, which is 13.2 actually. 13.2 was the reading, okay, for 8. So now I'm going to stop sharing the screen and go in here and put the temperature was 8 degrees and my reading was, did I say 13? I don't forgot even what I said. Was it 13? 13.2?
13.2.
13.2, yeah.
Okay, very good. So again, these are my numbers and my observations. Sometimes I'm probably not too careful with this one. Oh man, I probably need to change it with this one in here. Okay, I put 6.37. It rounded it to 6.4. Okay. So now I'm ready to basically. So you don't need too many decimal points. Okay, you don't need to have it 6. If it's 6.37, it's roughly about 6.4. Okay, so it's good enough for this experiment. So now I'm supposed to have finished this entire table. Please do not use these numbers because, first of all, I was not focused, honestly. So probably these numbers are not reliable. They probably are going to give me a lot of errors, okay? So I need you guys to be focused on this one in here while you're doing. If we were doing it in lab, we would be in partners, okay? Two people working together, and one person pays attention to this one and the other one pays attention to the other one. And because this thing can go quickly, you have to do it. Now, in between the readings, it is very important, and I try to simulate this lab as much as possible to the real thing. This is the old apparatus, basically. The newer apparatus is far fancier than this. And at least in another college where I was doing it, they have the new fancy one. It gives you actually the whole curve, okay? So you don't have to, you turn it on and the whole thing gives you temperature, and you really have, sometimes you don't even know how this thing is working. Okay, it looks like a simulation, honestly. It looks like somebody faked the numbers for you and make it work. Okay, so I'm going to turn on this thing just to illustrate a point in here. So right now it's 8. It was 13 point something. I have to wait for this one to cool down. I have to wait for the length to go back to its normal length. Okay, right now it's cooling back, so it's going back to its normal length, to the room temperature, whatever that room temperature. Now, when delta T is 0, that means it went back to its normal length. Okay? So that's what you do actually in the lab. And that's why for higher and higher temperatures, that's why we don't want to go too high. That time could be very long. I mean, it receives a lot of heat initially, but then when you shut it off, it takes a long time for it to cool. So in a real lab, this lab would have taken a long, long time. So, okay. So that's part of the thing that you would have to pay attention to. Also, don't start right away. In other words, oops, I got the wrong answer. Yes, between readings, you have to wait for it to go back to 0. Because if you drag it immediately, it's not cooled already. So it's not the same reading, okay? So always try to go back to room temperature. Otherwise, you have to read the difference in temperature from the last to the first and the length, and it's safer to wait for it to cool completely back to 0. When delta T is 0, now you're safe to go back into it and do it again, okay? If we're doing this in lab, you have to make sure that you're wearing the proper attire for it, including goggles and gloves and things like that, because this could really result in serious damage, okay? Fortunately, we're doing it on a computer. Any questions about the data collection? You're supposed to do 2 readings between 0 and 10, 2 readings between 10 and 20, 2 readings between 20 and 30, 2 readings between 30 and 40, 2 readings between 40 and 50, and you have to be very careful at that point because this thing could end up going higher. Let me show you. I'm going to wait for this one. Look at the furnaces, supposedly the animation trying to give you as if it's fire. So I'm waiting for it to go. The temperature is getting higher and higher. So whatever that temperature is right now, it's 30 degrees more, okay? That's why probably you don't have enough power in here to bring it to higher degrees in here. So right now it's 50 degrees more. So this is super hot, okay? Right now it's 70 degree hotter. So at this point, if I let it go, It's supposed to max at this point, okay? It's supposed to stop the animation. It doesn't make sense to go beyond this point, okay? So don't do that 85.4 degrees. That doesn't make sense, okay? So let's bring it down to 0 and wait for it to cool down. So again, this is just a simulation limitation. If we're doing this in lab, we have to be very careful, okay? Because this meter can go crazy in here, okay? So, any questions about the data collection? Yes, Amanda, you have to wait back for it to go back to 0 between each two readings. Doesn't matter if you're in the same range or not the same range. Jeffrey, were you going to say something?
Yes. Okay, so on the data collection, I know how we get the temperatures and the angle degrees. That makes sense. So on the right-hand side, it's the change in length over length not. How do we get that again? Or what
From
are those
Excel.
values?
That's from Excel.
Excel,
So once you take this data that you have collected, let's take the data if somebody remembers them and go back to Excel and see what Excel says quickly, okay? Okay, I'm gonna stop sharing that screen and share with you now the Excel file. If I do the temperature, remember the temperature now is sitting on the right, and oh man, that's exactly how the table looks like. So the degrees, I think the first one was 4 and the second one was 8, okay? And that immediately tells me how much delta L over L is. It's related to that degree. It's 1.406 e to the negative 10, to the negative 4. That means it's 10 to the power negative 4. That's basically what the E is, the exponential. How much was the temperature, the first one? Does anybody remember? Was it 6.37?
6.4.
6.4, roughly. And the second one was 13.2.
Yep.
Okay. So now, immediately, I got an alpha in here. And I got the delta L over L for these two measurements.
Wait, so the alpha, is it for both of those? Or
It's
is
the
it
same
just...
it's the material. It's the rod. The alpha for the rod.
So if you
One
click
alpha.
another box, will the alpha be different?
Yeah, it depends on the measurement. It could be different.
So if you click on 13.2, does the alpha change? That's my
Oh,
question.
no, that should not change. I mean, if you have another reading, the alpha may differ, but it's getting better and better reading, okay?
And so you want us to fill everything before we even do alpha?
Yeah, you're not going to get an alpha unless you're done. You're not going to get the correct alpha unless you did all of them, all of the 10 measurements. So this alpha right now is an approximate value, not the correct one. So if I come in here and it's giving me R equals to 1, that is nonsense because I only have 2 measurements. So this is not acceptable. R squared equals to 1. So if I come in here and put 1, the error is going to be 0%. That doesn't make sense at all. Okay?
Yep.
Because right now, the error, it says the R squared is 1.00 E plus 00. That means if I plug in that number in here, this is exactly what that is. That's what 1 means. It means that I have 0% error, and that is because I only have 2 points, okay? So if I did another one, let's say, for example, I don't know, 12, okay? And let's say the temperature, I don't know, was 17, okay? I'm not sure. So right now, the alpha has changed drastically. And it's the same alpha for all 3 of them. It's the same material, basically. What we're trying to find in here, the alpha, the linear expansion for the rod itself, okay? That's what that alpha is. Let's look at the R squared now. The R squared is 9.72 e to the negative 1, what is it, 1. So 9.72 e negative 1. Okay, now it's a better error. It makes more sense now, okay? So if I do another one in here, let's say, for example, I did another one and it was 17. I'm not sure, okay? This is just numbers I'm throwing in there. And the actual reading was, like, for example, the temperature was 19, okay? So now the alpha is 3.7 for all of these 4 measurements, okay? It's the same alpha for the entire material. And let's look at the E now. Now it dropped to 9.03, okay? So 9.03, 9, is it e to the negative 1? Yeah. Okay, so it's 9.03 e to the negative 1, okay, 0.1. So the error has jumped up now to 9.7%, okay? So those data I'm going to get from the tables in there, okay, from doing the actual activity. So I'm just throwing numbers in there that don't make sense. Let's say, for example, the next reading was 22, because again, there are increments of 2. And let's say for the temperature was, for example, okay, was 21 degrees, okay? Now the alpha is 4.32 e to the negative 5, okay? 10 to the power negative 5. Remember, let me stop sharing quickly here this thing with you so that we have the data. Yeah, alpha has a 10 to the negative 5 in it everywhere. Everywhere. That's what that E means. E to the negative 5 means that's 10 to the negative 5. Excel doesn't do 10 to the power. It does E, exponential, and the power base of 10. Okay? So that's how Excel represents the powers. So when it says 4.3, so it's even higher than that of lead. So the number that I got right now, remember lead is 2.9. So if I go back into my Excel spreadsheet, again, this is nonsense. This is not the real material. I'm getting an alpha that is 4.3, 10 to the negative 5. That is not the alpha for this one. Okay, some weird alpha, okay? It's not even that of lead. If you do this experiment carefully, you should find an alpha that is means something. So right now, the alpha, the R, has dropped to 8.7 because I added another number. Remember, the actual curve is this line. And I'm trying to fit it as a line, and it's not fitting at all. Okay? So right now, R is 8.79, e to the negative 9. So this number is, I can put it in here if you like. So it's 8.79 e negative 1. And now the error jumped to 12%. Okay? So again, this data is unreliable. Do not use it, okay? Do not rely on it because it doesn't make sense. But what I'm saying, since you asked me, Jeffrey, about delta L over L dot, you get it from Excel. It's these numbers that are popping up in here to the right. Do you see them?
So those numbers on the right, we're putting those into the last column of the table in the lab, correct?
Yes.
Okay.
Okay.
As it's written, so it'd be that whole number. It was like 1 point something E.
Yeah, E or 10.
Okay.
10, actually. That's how we do it normally. But if you want to put it E, that's fine too. Okay? 10 to the power negative 5 or 10 to the power negative whatever that number is. Okay?
Just moving the numbers over from one table to another.
Yes. Okay?
Okay.
So, but this advantage of this one, it's not just that. It's going to give you alpha. Okay? It's not just these things in here because it's going to give you the alpha. Otherwise, that PDF file is basically you're supposed to do the calculation for you guys by yourself, okay, to find the actual alpha and the dependency and do the fitting, and it's really a lot of work. Excel is basically saving that headache for you guys, okay? So it's doing the heavy lifting for you guys, doing all of these calculations to give you delta L over L naught. And then it's going to give you the actual thing that you're after for the lab, which is the linear coefficient of thermal expansion for this material. Obviously, the R squared is needed to find the error. Now, here is the trouble with this whole lab, okay? From table 3, how high was the error? So you need to read this number, and you tell me how high the error is. Now, if the error exceeds 5%, you need to do the whole thing. You need to go back and collect the data again because that's not acceptable. So make sure this data gives you an error less than 5%. You have to be careful. That's question 4. Does this make sense to you guys? Do you guys understand now what's at stake? When you do those observations, you really have to be careful with them. And after you collect the data, you go back into the Excel. And Excel, after you get the R squared, you plug in the R squared. And that gives you an error from Excel. At that point, look at that error. If it's too high, if it's 7% or 13, like I had 12.9%, that is a time for me to go back and redo the observations, okay? So there's something went wrong. Actually, sometimes if you're trained enough, you will look at the data and you see which one is probably messing the reading for you. Most of the time it's this readings, okay? The beginning or toward the end. usually this side, this point is mess up data for you. That's why you have to be careful not to exceed that, not to reach the 50 at least. And in here, you have to at least get it clear out a little bit, okay, to do the readings. Most of the time, that's the culprits, but not guaranteed. So you might have probably did not read the data correctly somewhere, and you get a higher error than this one, okay? If you are running to this lab again and again and again, and you're getting higher and higher errors, and you were not able to get it into wraps, please let me know throughout the week that, hey, I tried this one 3 times or 4 times, and I'm not getting any errors that is less than 5%. Please let me know what's going on. So we go together and we see what went wrong, and probably you're transcribing the data wrong. That's all in the Excel spreadsheet. Maybe your data collection was correct all along. Do not delete the data. It's a good idea to write the data on a piece of paper, separate piece of paper, because you might not need to do everything all over again. So once you collect the data and you put it on the PDF file, it's a good idea actually to put it on a separate piece of paper next to you, so that the data is actually, you can come back to it and see if that becomes useful. As a matter of fact, one of the things that is really important for an experimentalist, a person who does experiments, is the data. The data is something extremely valuable. It has a lot of value in it. So you don't want it to be wasted. Once you collect it, it's basically extremely valuable. So you don't want to really throw it away just because you think something went wrong. Maybe just one thing, minor thing. And sometimes you learn a lot from that piece of data. So don't throw it away. Just go back and see if you can collect new, fresher data and see if that makes a difference. So when you call me, or I'm sorry, when you send me a message, I'm going to be asking for the, you said you did it 3 times. Can I see the 3 sets, okay, to see what went wrong? Maybe the first was good all along. Maybe there was only, you did not enter it correctly in the Excel file, and that's why you're getting very high values of R squared, which led to a huge value of the error, okay? So maybe you had a good values all along, but maybe the way that you were doing them. So we just have to go back and collect, and you don't have to collect. You don't have to spend maybe half an hour doing this with me. All we have to do is just put it, enter it correctly, and you're done. Does this make sense to everybody? Yes?
Yes.
For question 4, please keep your data. Don't throw it away, okay? And if it succeeds from the first time, you're good. Just submit the thing. If it doesn't, I will need those data. Okay, question 5. Now, once you find alpha, you're going to go back to the table, to this table that has alphas in it, this one, table 2. And you're going to tell me which material that is. Was the alpha close from this number, or this number, or this number, or this one, or this one? And if it's close from, for example, from 1.76, let's say, for example, it's 1.8 or 1.7, then I can safely say that this is actually made out of copper. Okay, if it's 2.93, for example, then I can safely say this is lead actually. Or if it's 2.9, that is lead. Okay, so that's basically what that last question was. Is based on your table, based on your data from table 3. No, based on your, what was the value of the linear expansion? And here you said linear expansion is so and so times 10 to the negative 5 per degree Celsius. That's the unit for it. Remember, alpha is measured in per degree Celsius. Okay. And I think this material based on table 2 is, and you're going to tell me what that material was. So it's a mystery material at this point. We don't know what it is. And as usual, your conclusion. Any questions? If you guys don't have any questions, you know what you're supposed to do. You have 3 or 4 questions before the 3 questions before the actual activities. You have 1 activity at home and another activity on GeoGebra, and you're supposed to do this lab. I'm hoping that should be easy enough for you guys to do. The biggest task actually for this lab is collecting those data. Okay. Once you do that, the rest should be easy, should be straightforward. The Excel file should help you a lot. Any questions? Okay, if you guys don't have any questions, what I'm going to do is I'm going to basically stop the recording and then turn off my camera and my audio, change the speakers, basically the audio set, so that I can move around too. And if you guys have any questions, please ask it. I can hear you, then I can come rushing to the computer and basically work with you guys if you choose to stay here. If you don't want to stay here and you would want to work on it by yourself, that's fine too. And you can ask these questions. Oh, the question of the week, I forgot to say that. It's about the Excel file, okay? It's very important to upload the Excel file. That's a very good question, okay? Because this is different from before, okay? So you have to download the file, save the file after you change it, and then open it, and then upload it. That is a question that I had all along in mind. Okay, thank you very much, Alicia. Does everybody understand what we're talking about in here? So I want to make sure that you guys are understanding of what needs to be done today. Today, which is a little different than previous stuff, we have an extra file that we need to change, save, make sure the saves changes persist. Yeah, that means they are saved. So that once you guys upload it, I have the data that you have got everything from it, and to compare it to your file, PDF file. Thank you, Alicia, and everybody else. So I'm gonna stop the recording now, and if you guys choose to stay, that's good. If not, I'll see you guys in a week time. Yes, you need to submit the Excel file. It's actually graded, it's part of the rubric. Toward the bottom, it says that the file has been submitted and has all of the data in it. Does this make sense to you, V? Does this answer your question, I should say? Okay, very good. So, see you guys. I'm gonna be here, but for those who choose to leave, I see you guys in a week.